Good morning.
Good morning, dear.
Good morning.
Good morning, dear. Bye, Medina.
Hi. Good
Hi, dear.
morning.
Good morning, dear. Okay, Brian. Here goes. Good morning and welcome. And now, before I start with, should I say the new chapter, any questions? Any questions about chapter 1 and 2?
Yes, I have a question.
Go ahead, my dear.
For the pressure and area,
Yeah,
I'm a little confused about that one and the equation that it should be using.
the equation is straightforward, my dear. Listen. There's no, like, now when we say that pressure, what was the definition for pressure? Is the concentration of force per area. Clear? Now we can say that, okay, you know, the unit for area, that's going to be, it's okay, any unit of distance squared. Clear? And what's force? The unit for force was going to be newtons. Clear? So the equation for pressure actually, it's okay, comes from the definition here. Okay. Now what remaining can say that, okay, as in this equation or this definition here is that you were force, that is the numerator. That mainly means that that's going to be as okay directly proportional to pressure. Clear? But this is only going to be the case that's okay if the area remains constant.
So like if the area stays the same, like it doesn't move up.
If the, yeah, listen, okay, you can say if the area stays the same. Right, okay. And that's what you mainly as okay will have to do to, you can say as okay, establish the actual relationship between force and pressure. Because if you keep on changing the area as well, that is going to affect what you calculate as a pressure, right?
Yeah,
Clear? Okay, if you keep on, yes, okay, if you're changing, yes, okay, both the force and area, they're going to have, yes, okay, their own effect on the pressure. So mainly as okay to establish as okay, what is the actual relationship between pressure and force. But that you have to keep the area constant. Clear? Likewise, when we said that, okay, yes, we want to, yes, okay, establish the relationship between pressure and area, which was inversely proportional. In that case, that's okay, what was it that we did? We kept force constant. Because if we change, that's okay, the force, as we change the area, that's going to, that's okay, both are going to, that's okay, have their own effect on the pressure. So mainly as okay to establish the actual relationship between area and pressure. We need to keep area, or we need to keep the pressure, force constant.
okay.
Okay. But the relationship, my dear, is okay, that is pretty much straightforward, yes, okay, from the definition.
Okay, thank you.
Okay. So yes, okay, if you want, yes, okay, establish the relationship between this and this, you're going to keep this constant. You want to establish the relationship between this and this, you need to keep this one constant.
And then in an equation, they'll tell you like which one is constant, right? Or,
No, they were not changed. Just look at the question that we had in the book.
okay,
And then what did they do? They changed both of them, right?
yeah, it was confusing.
Okay.
for me.
So both of them were as okay, changed 3 times. Or increased 3 times, right?
Mhm.
Clear?
Yeah.
Okay. So the time that, okay, yes, you can say, okay, you only increase the force 3 times and the area had remained unchanged. Then the pressure was going to, yes, okay, be 3 times greater, or also increase 3 times. Whereas they kept the pressure or force constant, but increased the area 3 times, then okay, as the force was, or the pressure was going to, yes, okay, be 1/3. Or decrease to 1/3 of its original.
So when you're decreasing, you normally use a fraction, like of
When you
the,
decrease a thing, it's going to be a fraction, right?
yeah,
How big or small of a fraction is going to be 1/3? If you increase the area 30 times, it's going to be 1/30 of the original. Look here then. Okay. Now we can say it's okay, we may have, okay, as a pressure or initial pressure. We can say it's okay because it's okay, our force was 10 newtons or an area of, okay, as 5 centimeters square. What is it that our pressure becomes in this case here, or is in this case? We can say it's okay, this would be our initial pressure. That's going to be, okay, 10 divided by 5, which is 2 newtons per centimeter square. Did that make sense?
Yeah,
Good. Now what we say is, let's just say that, okay, as we increase the pressure, that's why the force. The force is, let's say, it's okay, increased 2 times. Area is not increased, or is not changed. Okay, now these are all clues that you're going to get out from the question. It's going to be written in the question. So you pretty much actually, okay, pick up the information that you get from the question. And okay, as then put that into your equations or whatever you want to do. But yes, okay, what do we do? Yes, okay, double the force. So our force is now going to be, as okay, 20 newtons. But we said, okay, as we kept the area constant. Or the area didn't change. So what is going to be, as okay, our force now, pressure now, is going to be, as okay, 20 divided by
5.
but which is 4 newtons per centimeter square.
Yeah.
So in this case, what did it say is, okay, what would be the option? It's okay, did the force increase 20 times, 50 times, whatsoever. Here it's okay, it doubled. Because you can make straight this up for say that okay, 4 is twice that of 2. So before we start off with a force of a pressure of 2 newtons per centimeter square. Now we have a pressure of 4 newtons per centimeter square, which mainly means that okay, yes, it's the same centimeter square. But yes, okay, here is only going to be as okay, force of 2 newtons per each centimeter square area. Where here is going to be as okay, a force of 4 newtons per each centimeter square, which mainly mean that okay, here there is going to be as okay, greater force or greater pressure, which is going to be twice as what we had in the beginning.
Okay.
Clear?
Yes.
Now, well, it will be the opposite with area. Now, if you yes, okay, you can say okay, double the area. With all yes, okay, doubling the force. The force remains constant. So what are we going to have now? Yes, okay, we started off with okay, yes, 2 newtons per centimeter square, right? Okay, because 10 newtons per 5 centimeter square is 2 newtons per centimeter square. But if we double it, what it's going to become now is going to be, it's okay now, 10 newtons
Over.
per 10 centimeter squares, because we double the area, right?
Yeah.
So 5 times 2 is 10. What do you get now? You get, okay, yes, 10 divided by 10 is
1.
1 Newton per centimeter square. So your initial force or your initial pressure was 2 newtons per centimeter square, but you double the area, so okay, it becomes half.
Okay.
you increase it, let's say it's okay, 20 times. Okay, then you will say, well, okay, yes, you have, okay, yes. The equation is going to be as okay, 10 divided by 100, which is 0.1. So now it's okay, meaning because you increased area 100 times by keeping it okay. The force constant is okay. In this equation here, okay, becomes just okay, 0.1 Newton per centimeter square. But simply just okay, just a matter of okay, as dividing the force by the area.
Okay,
That will give you just okay the pressure.
and then your
The
final.
less this
answer-
number is, the lesser will be the pressure.
Mm,
The greater the area is, the lesser will be the pressure.
And then the final answer always has to be Newton centimeter square.
It doesn't have to. It depends upon as okay what the question asks you. If it asks you as okay, what is your final pressure? Then okay, yes. Then you have to just okay go with okay first of all one which is numerically correct and which has the correct unit.
Okay,
Because there may be as okay other answers which also have okay as 0.9, but it may give you as okay a different unit. If you choose that one, all is okay numerically is okay the answer is correct. But you choose the one that okay it's a different unit. You can say centimeter per whatever, kg per whatsoever second. Let's just say that you choose that one. That may mean that okay, you think that this centimeter per kg per second is the unit for pressure, which is wrong.
okay,
Clear?
Yeah.
Okay, so it's not only going to be good enough to just okay, choose the numerically correct answer. If you choose one with the wrong unit, your answer is still wrong.
okay.
But the unit, my dear, is pretty much okay, it's straightforward here.
Yes.
From the definition. You just have to know okay, what the unit for force and what's the unit for area.
Okay,
So even if it says yes, okay, 0.1 newtons per centimeter, that's wrong. Even if it says okay, 0.1 newtons per centimeter cube, that is wrong.
Yeah.
Because then this will become volume. This would just have been okay, a simple distance.
Okay,
So the Armenians, okay, I told you yes, okay, the Armenians, okay, just a couple of things that okay, yes, you have to, yes, okay, check. What's first of all, what's the definition of the parameters or variables or whatever you want to call them? Clear? Okay. What is going to be as okay, the unit? Clear? Okay, and you can say as okay, what are going to be as okay, the relationship between as okay, the factor variable and okay, as the things that determines it. Clear? What's the relationship between pressure and area? What's the relationship between pressure and force? But what is that pressure is? You have a big or smaller rock in your backyard and you want to move it. You want to move that rock. Okay. Now, whosoever comes and applies a force on it, pretty much okay, has to push on it. That amount of force that they apply onto is okay, a square inch of that piece of rock is going to be called the pressure.
Sorry, could you say that again?
No, It's not for you.
Yes.
Clear?
Yeah.
Okay. So if it is a small rock or smaller piece of rock, and okay, as I apply greater force. In physics, yes, okay, that will be yes, okay. A greater pressure is being applied onto that rock. Okay. Now I can immediately says, okay, how is okay, all dependent upon how badly it is stuck to the ground. Okay, I may have just okay apply a greater force as okay, you can see a greater pressure.
Yeah. Okay.
Anything else?
I have a question.
You'll get them. Yes.
Could you like make a practice worksheet for us with problems from like density, pressure, and distance?
My dear, you just change on the numbers. Like, okay, we can have one right now. Okay. So we can see. There's a pressure of water particle. Good. What will be the final pressure? Here we go. Have fun, and you have 2 minutes. So the pressure applied, or there's a pressure of 20 newtons per centimeter square applied to a particle. What would be the final pressure if the force is increased 20 times and the area is decreased to the half?
I got I got 40 Newton centimeters square. No? Okay. Can I answer?
Go ahead.
I got 40 Newton centimeters square.
Okay. Anybody else? There's a pressure of 20 newtons per centimeter square applied to a particle. What will be the final pressure if the force is increased 20 times and the area is decreased to half?
I got 40 as well.
Okay,
Isn't it increased by, you're supposed to add it? I thought you were supposed to multiply it, because it's increased by 20.
exactly.
So that's 400.
20
And half of that
times.
is-
What does times means?
Yeah, so that's 400, and half of that is
Huh?
isn't that, wait,
Yeah, but even if you multiply 20 times 20 times 20, it's 4.
20 times 20 is what? This is a lie, girls. 20 times 20. It's straightforward. It's 2 plus 2, or 2 times 2
Yeah,
is
it's
4.
400.
And then you have 2 zeros.
Yeah. You're making me second guess my multiplication. And then you divide it by 10, right?
Why? Why do you
Because-
multiply divided by 10?
Because you said the area is decreased by half.
So first you had 1 centimeter, right? Okay, this is what we said.
Yes.
This should be understood as 20 newtons for 1 centimeter square. So this actually becomes 400 divided by a half. So your final force is 400 divided by a half is 800 centimeters per 800 newtons per centimeter square.
So where I am confused now is, so when they said it's decreased by half, we have to
You reduce the area
reduce the area by half.
Hmm.
We have to
Yeah.
put half.
But
with
it's still
the
asking you, what will be the final pressure?
pressure. So we have to write it as a decimal in the equation, because where I put 10 is because.
Okay, so you divide 400 by a half.
Okay,
Listen, you divide 400 by 1, what do you get?
400.
Exactly. You divide 400 by 2, what do you get?
800.
You divide 400 by 2,
No, sorry.
800.
Yeah.
Okay,
200.
exactly. Now, if you say yes, okay, I have 400
Mm.
and I divide it by a half,
Mhm.
you're going to have 800. So in this case, okay, your final force will be it's okay, 800 newtons per centimeter square. Or you can say it's okay, it would have been 400 newtons per half centimeter square.
I have a question.
Yep.
So when you're asking us, when you give us like original pressure and you're asking us to increase it by whatever number, we're gonna be multiplying
Exactly.
number you asked us to increase it to the original number?
Yeah.
Right? And then when you ask us to decrease it, what do? We divide it by the original
You
number?
divide.
Okay, all right.
That's unless, okay, it's going to be something because yes, okay, what is it you can say, okay, increase, there could have been, okay, increase by a factor of 20 times. But then I would not have wrote 20, or then I would not have wrote times. Now, usually that's okay when you says, okay, decrease by a factor of, decrease by 20 times, it automatically means this times here automatically means that it's going to be multiplied. There's no question about that. And directly speaking, girls, that's okay when you say decrease by half. Decrease by half automatically means that you divide. But if I say that's okay, increase by a factor of 20, I don't have to write times because that's okay. By the factor automatically would mean that's going to be multiplied. Or it's going to be, it's okay, be a replacement 4 times.
Can we have another one?
Hmm.
Can we have another equation? We need more, I need more practice because I don't know.
Yeah, because, okay, I better keep my mouth shut.
Thanks for the confidence. What does the bottom say?
Just a sec. I'm going to read the question. Now, this is a 2-in-1 question. Okay, girls? Now, what it says is, if a force on a particle is 16 newtons and the area is 4 square centimeters, what is the pressure? Okay. Now, the next part says, now if the force is increased twice or 2 times, and the area is decreased to 1/4, what is the final pressure?
What did you say about the area?
area is decreased to 1/4.
Okay, thank you.
Yes, girls.
I think I got it. But,
Okay.
but if everyone's not ready, I don't want to give the answer yet.
Okay, you can still give the answer. I don't know.
Well, for the first part, I got 4 Newtons/centimeters squared.
Mhm.
And then for the second one, don't think this is right, but I got 128 Newtons/centimeters squared.
Okay,
I got the same thing.
okay.
I didn't get that.
You didn't get that. Okay.
I got
What
the,
did, Esther, what did you get then?
So I did 16 newtons times 2, and I got 32. And then for the area, I did 4 divided by 1/4. And so I got 2 answers because I didn't know if that equaled 1 or 16, since it's like a reciprocal. So the first answer was 2, and then my second answer was 32.
No, your first answer is wrong. That's why your second answer became wrong too.
Okay.
I got 4 newtons over centimeters squared for both of them. I don't know how for the
I
second.
don't know either, my dear.
Because I
Okay,
did
listen,
4
okay,
times-
girls, here. The first one was, there should be no ifs and buts about that. It's mainly as okay, just that we have okay as the force is given, which is 16, And we have, okay, as the area as well is 4 centimeter. Yeah, don't go by the square and so on. So that's mainly, that's okay, going to be the unit of area. There's no multiplication or so on, so applied here for that. Clear? So what the media is, okay, just are asking us, okay, what is the pressure? So here is, okay, the pressure is going to be 16 divided by 4, which mainly becomes 16 divided by 4 is 4. So we have, okay, as a pressure of 4 newtons per centimeter square. Clear? Okay. Now, we can then say "16 newtons okay, is going to be doubled. So what do you get? 32 newtons. Clear? We had an area of 4 centimeters square. Clear? And that is going to be watt. Okay. But mainly it's okay here in the relationship, that will mainly mean that, okay, yes, you will actually, it's okay, multiply this by this to get the final pressure. So that's how we got, okay, it's 28 newtons centimeter square.
Is it because the 4 centimeters square and the 1/4 is reciprocal?
Yeah, exactly.
All right, that's why I messed up at. Thank you.
Wait, so would it be okay if I did 32 divided by 0.25? Like just,
Yeah,
That's
it's the
right.
same. Listen, 1.4, what does 1.4 mean? It's just a quarter, right? Okay, but that's mainly as, okay, just written as a fraction. Another way of saying is, okay, a fraction, or okay, a quarter is 0.25. So whether you multiply 32 by 4 or divide 32 by 0.25, it comes out to the same.
I'm a little confused.
Can we please have math homework? Please.
Look at the program problems in the book and play around with the numbers.
is it just because you said, you didn't ask us to decrease 4 divided by 0.25, you just gave us like 0.25 or 4 or whatever as the new number?
This, the same idea. This is a fraction. So what does it mean? Just okay, decreased to 1/4.
So now it's, yeah, okay.
When you decrease the area, that's pretty much okay what it tells you. You decrease the areas, okay, the pressure is going to increase. Even if you kept the pressure or force constant. If you say, okay, there's no change in the pressure or force. The pressure. Now, if you don't change the force, but yes, okay, we reduce the pressure, what's going to happen? The pressure is still going to increase if we decrease the area. Because pressure is reciprocal to area. Not reciprocal, inversely proportional, sorry. Okay, so 1/4, and that's why I said 1/4, that is mainly as okay, just a fraction. Expressing as okay, then that's okay, a decimal value of a whole. Which means as okay is going to as okay can also be written as 0.45 or 0.25. Which means okay, is just going to be as okay, the same value expressed as a decimal. Now you can take any number. Okay, we can say 20, we can say 20. You multiply 20 by 1/4, or you multiply 20 by 2.04 or 0.25. The answer is going to be the same. Five. Here you may as okay, for this one you may say it's okay 5.00. But these zeros here actually is okay, don't have any word. Oops, sorry. So it's okay as far as 0.4 is concerned, or 0.25 is concerned. They work the same. Just like you can say as okay, 1.2 is the same as 0.50. Or you can say, roughly speaking, as okay, 1/3 is the same as, sorry, 0.33333 or so. You can go as okay, 1/8 is the same as okay, 0.125. So whether you say it's okay, 20 multiplied by this or 20 multiplied by this, the result is going to be the same. You go 20 multiplied by this or 20 multiplied by this, the result is going to be the same. You go 20 multiplied by this or 20 multiplied by this, the result is going to be the same. The only difference here is that, okay, this is a number expressed as a fraction, this is a number, the same word, just okay, expressed as a decimal number. So when I say it's okay, I guess it's okay, decreased. Now, most likely it's okay, whenever it's okay, it says decreased, it's going to, it's okay. Most likely it's okay, be a fraction. Unless, okay, as that, okay, as whatever is decreased in a way that, okay, as we actually, as okay, decrease it by subtracting. For me, that's okay, because it's okay, in the equation, it's okay. It's a number here and a number here. If this increases, it's going to increase by, or decrease is going to, it's okay, increase or decrease by multiplication or subtraction or division. Likewise, okay, this may be doubled. This may, it's okay, increase 4 times, 6 times, 8 times, or can decrease. Yes, go.
I find this like really confusing, like the increasing and decreasing. It's just, for me, it's just like the first part I got like super quick. It's just,
Okay. But listen, dear, okay. And that's why it's okay, understanding the relationship will make it more easier.
I have a question too.
You're good.
About this problem that we just did. So if the force increases 2 times, so that means that new pressure will increase in 2 times 2, right?
Hmm.
And then area decreases in 1/4. It means like that new pressure will increases in 4 times. So,
Yeah.
so then pressure, new pressure, final pressure will increases in 8 times, right? Total. 2 from the force and 4 from the area.
Pretty much.
So it 8 times. So if we found that initial pressure was 4 and it increases 8 times, so my answer was still 32.
Important. Yeah. No, that's going to be too much, my dear. Let's look.
If force is increases in 2 times, then pressure increases in 2 times as well. So it was, how much it was? We found it was 4, right? The initial was 4. So it became A 2 times, increases 2 times. So it became A, because we found that pressure is 4 Newton per centimeter square from the first part of the problem, right?
Yep.
So if force increases 2 times, so it becomes like A Newton per square centimeter.
Mhm.
And then area decreases 4 times, I mean 1/4, which is makes the pressure increase in 4 times, right? So if
Yeah.
it was A and then increase in 4 times because of the area, so it's 32.
Yeah, okay, maybe okay. Let's just do another one there. Let's look, let me make it simpler. So pressure, let's see. The initial force applied is okay. We can say, okay, yes, what is the initial pressure?
Or
Okay. Now, if we increase the
it's 2. The final pressure is 2.
now just look here. Clear? Now we can mean says, okay, that would be it, but we can calculate it out to become 4 newtons per centimeter square. Clear? Did that make sense?
Yeah.
Good. Now, we can say, well, okay, yes, we keep the same pressure. "20 newtons per centimeter square, or 20 newtons, right? Okay. And we double the area. Okay. So you mean it's okay, we'll have 5 multiplied by 2, which gives us, okay, as a total of 10 centimeters square.
Right.
Now, what's the final pressure then?
2.
Yeah. Now, had we let's say it's okay, reduced the pressure, force, sorry. To let's say it's okay, 1/5. Okay. Then we combine it says okay, this part of the equation here will now becomes okay as it'll mean that okay it's 20. That's okay, multiply by 1/4, which is the same as saying it's okay, 20 multiplied by 1 divided by 5. Okay. But now in this instance, okay, here our force would have been 4 newtons. Clear? Now this 4 newtons is okay. Now it's okay divided by 10 centimeters square. Then what would it be then? 0.4 newtons per centimeter square. Or it could have been okay. But the bottom line is now it's just going to be as okay, all dependent upon it's okay, how much the force increase or change, how much the area change. Now that's going to be as okay, hopefully as okay information that you'll find in the question. Okay. Now all dependent upon is okay, the options, because it's okay, they ask you, it's okay, where is the final pressure? Then it's most likely it's okay, then going to be it's okay, you can say it's okay, numerical value is okay with the correct unit. Whereas if they say it's okay, where is going to be as okay, the change in the pressure, then it may as okay be that okay, as the pressure is increased twice, 20 times, 15 times, and so on. Right? But you mean that's okay, well, it says okay, how to compare it's okay, the initial pressure to it's okay, what your final calculation gets to. So if you had okay as a initial pressure, which was let's say it's okay 20, and you okay as end of it okay as a final pressure which is 80, you still have to say okay, now it's okay, the pressure increased 4 times. Why? Because 80 is 4 times greater than 20.
What pages are the equations on in the book?
Equations?
Yeah, for pressure and density.
It's in chapter 2.
I did the equations in the book, and can we have like at least a little bit of homework? Cause to practice at least to get better at it.
My dear, you just put random numbers. Like, okay, I can go on from now till doomsday.
Okay.
It's not going to take us anywhere. Like, oh shit. The equation there is, and that's why I says, okay, the equation is pretty much okay as obvious from the definition. And okay, so is the relationships. Even if I wanted to, yes, okay, I can't change it because this is something that already is okay, has been determined. Yeah. So if force increases, pressure increases. When area decreases, pressure increases. And then you can just go opposite. If you decrease the force, that will lead to a decrease in pressure. Where, okay, if you increase the area, that's going to lead to a decrease in pressure. But this kind of relationship, that's going to be as okay, the standard. Because if you just take another one and say, it's okay, density. Now, what was density? Even if I wanted to, I can't change the definition of that. Or as okay, the formula or the equation. Because okay, here is just going to be as okay, mass or volume. Clear. So the relationship here is going to be the same. That okay, as an increase in mass is going to as okay, lead to an increase in density. Where okay, is going to be a decrease in the volume that will increase the density. And vice versa. If you decrease the mass, that will decrease the density. If you increase the volume, that will increase the density. Now, please keep in mind, go just okay, when we say something like this, that increase in mass, increase the density, that's okay as if you keep volume constant. That means okay, just establishing as okay, the direct relationship between density and mass. Where we say it's okay, an increase in volume decreases the density. That's mainly as okay, just going to be as okay, or vice versa. It's going to be as okay, a direct relationship between density and volume, where in which case it's okay, mass is kept constant. So whichever case it is going to be as okay. We can say it's okay. Or cookies per student is going to be determined by what? Because there's a number of cookies in the box. Divided by, okay, the number of students. in the class. If somebody say, well, okay, I don't like cookies, well, you can take apples, you can take oranges, you can take whatever. But we can say is okay, if you keep the number of cookies constant in the box. Let's say it's okay, we had 20 cookies. We started off with just, let's say 10 students. What do you have? It's going to be, it's okay, 2 cookies per student. Now, if he has, okay, it's the same number of cookies, but we increase the number of students 4 times. What are we going to have now? It's going to be, it's okay, now a total of 40 students. And we still only have 20 cookies. So what are you going to have? It's going to be 20 cookies divided amongst 40 students. So how many cookies will each student get? Half a cookie. Did that make sense?
Yeah.
Good. Now we still say it's okay that we start off with the same number of students and same number of cookies. So initially that's okay, each student will get 2 cookies, right? Clear. But what did we get? Okay, we said here it's okay, we increase the number of students. We ended up with that's okay, less number of cookies per student. Okay. We said okay, it was a half cookie. Because okay, we increase the number of students by twice. Now, if we just keep the number of students constant, still at 10, but we has okay, increase the number of cookies by a factor of 5. What is going to be the case then? You can say it's okay, we end up with 100 cookies and we have 10 students. So each of you girls are going to just okay, walk home with a total of 10 cookies. So what did that tell you? That the number of cookies that each student get is going to be as okay, directly proportionate to the number of cookies in the box. But it's going to be okay, be inversely proportionate to the number of students. Here you can say it's okay, we increase the number of cookies 5 times. We increase the number of students twice. Now, if we do both increase the number of cookies per case or in the box, and also it's okay, double the number of students, then you're going to end up with okay, as a, because okay, we take say both of them changed. This was going to be as okay, a total of 20 students. And we have okay as 100 cookies. Okay, so we have okay, a total of 100 cookies. Now it's going to just okay, be distributed amongst 20 students. So you're not going to walk home with half a cookie. You're not going to be walking home with 10 cookies. You're going to walk home with 5 cookies. Now you can just do the same thing with, okay, as with your mass and pressure and density and volume and areas. Whether you are being given, okay, as an initial pressure, saying, well, okay, as this was your initial pressure, or this was the force, this was the area, as okay, calculate out the pressure for yourself. And from there, it's okay, so we'll increase this 4 times, increase this 2 times. We decrease this to 1/10, we increase this 100 times, or whatever. Mainly because, okay, these are things which are, okay, as multiply and divided. Increase mainly as, okay, is going to mean that, okay, as it will be multiplied by the initial. Decrease is mainly going to mean that it will be divided. Or reduced. So reduced by a factor, increased by a factor. In chapter 1, I think exercise, there was a question where they talk, in one question they talk about, is, okay, increased by a factor of. Now what that increased by a factor means was that you multiply. Decrease by a factor mainly means that you divide. So decrease by a factor of 5 mainly is going to be the same as, okay, yes, dividing by 1/5. Did that make sense? Okay. But if it says, okay, that, okay, we decrease the area by 2. That decrease the area by 2 is not going to mean that's okay if you have, let's say, it's okay, an initial area of, let's say, 10 centimeters square. Then we decrease it by an area, or we decrease it by 2. It's not going to mean that, okay, 10 minus 2 is going to see as, okay, decreased by a half. It's going to be decreased to it half its initial. So that's mainly, that's okay, just wording that, that's okay, you have to, that's okay, be able to pick that out from the wording of the question. So you can say, okay, this is grammar of math. Yes. So mainly because here it's okay, the factor or parameter that we are calculating is determined by multiplying and dividing. Pressure increases twice. Or force increases twice. pressure is going to be doubled. Area reduces to 1/4, pressure will become 1/4. It's going to be, yes, okay, become a different thing, yes, okay, when we subtract and add. That's going to become relevant in chapter, well, okay, even in chapter 4. Because, okay, this parameter here is not got determined. Or we don't get it from, yes, okay, multiplying and dividing two numbers. We get it from, yes, okay, either subtracting or adding up two numbers. Did that make sense? But for now goes, this is the basic relationship. Okay, so whether it's mass, whether it's force, mass is going to, yes, okay, increase the density. Force is going to increase the pressure. Whether it's volume for density or area for pressure, when you increase the area, the pressure will decrease. Now that's provided that force is kept constant. If the force also changes, okay, that's going to have its own effect on the pressure. Just as we did here. We only change one. We only change one. The number of cookies that each student would take home as okay was going to be different. Whereas okay, as we changed both of them, it's going to be okay, a whole different number. So take a small 20 minutes break, go back, look at your pressure definition, the equation, look at your density and the equation. Okay. And okay, yes. CU goes at 12:50, not 12, sorry, 10:50. Yes, girls. Welcome back. Any questions? Are you still confused about the relationships? Still any confusion about the relationships? Okay, can we start with chapter 3? Any objections? Oh, yes, okay. They just named it, okay, describing sound waves. But what this chapter here is, okay, main is going to be about is going to be, it's okay, working says, okay, or 7 acoustic parameters. That's mainly, it's okay, what we will talk about. Clear? And we already said, okay, as the 7 acoustic parameters that we had were period. We said frequency. We say wavelength. We can also say it's okay, intensity. Power. And amplitude, and the last one is going to be the propagation speed. Okay, now goes when we will talk about these 7 acoustic parameters here individually. It's okay, they're going to mean it's okay be 5 points that we're coming across for each of them. One is going to mean it's okay, be it's okay, what will be the definition? What is going to be it's okay, the unit? Now, for some of these acoustic parameters, it's okay, they're going to, it's okay. All of them have, okay, as we can call it, it's okay, typical value. Now here, it's okay, this typical value, that's going to be, it's okay, the typical value of whatever parameter that we are talking about in relation to ultrasound. Here, the typical value of any parameter that is being used, okay, accounting for the ultrasound. Another thing is going to be, okay, what determines our acoustic parameter here. And okay, so this an acoustic parameter that can be adjustable, which mainly means it is something that can be changed. Then it is adjustable. Where, okay, yes, if it can't be changed, then it is not adjustable. Yep. After that, once we are, yes, okay, talked about at least, yes, okay, 2 or 3 parameters, we may go and say, okay, these parameters here related to one another. And if they are, what kind of relationship would that be? Clear, very command says, okay, a relationship could be directly proportional. A relationship can be, yes, okay, inversely proportional. And a relationship can be, yes, okay, even if it is inversely proportional, yes, okay, some of those inversely proportional relationships may be reciprocal. Okay. So that's okay. Again, yes, okay. At the bottom line, it's still better come out to, yes, okay. Are these parameters here related? Okay. If they are, what kind of relationship is it? Where you says, okay, if they're not related, then okay, yes, it doesn't really matter whether yes, okay, you change one, whether you increase it or decrease it. Clear? It is not going to have, okay, it's any effect on, let's say, yes, okay, this one here. Or this one here. Okay. So that's pretty much okay as what we may be. It's okay trying to start. Now, what I said earlier is okay, or last week in relation to is okay, our sound waves or sound as a generally. There was going to be source. Now here is okay in this chapter, unless okay specified otherwise. Is okay. Source will be it's okay the transducer. But for some of the parameters, source is not going to be transducer, but it's more going to be it's okay the system. Maybe can mainly says okay your transducer that's going to be it's okay that little joystick that you will be holding in your hands and okay as rubbing on the patient's body, all depend upon is okay the area that you scan. Whereas if we say system, that's going to be as okay that big piece of machinery. Clear? The other thing was going to be as okay be we could say as okay medium. And as far as we were concerned, yes, okay, we mainly yes, okay, only have one type of medium here in ultrasound. And that's going to be as okay, the human tissues. Okay, so these factors, yes, okay, or these things here. That's mainly as okay, going to yes, okay, be discussed when we say it's okay, determined by. Is this factor here or parameter, sorry? Is that determined by the source? That mainly mean, okay, this parameter can either be as okay, determined by the transducer or by the system. There's going to be as okay, the transducer that will determine is the period, is the frequency, is so on, so on, so on, going to yes, okay, be more or less. Or yes, okay, the system. Is it the power? Is it the intensity? Is it the amplitude of the sound wave produced? In this case here, is going to mean it's okay, be determined by it's okay, the setting of the systems. Okay. Any questions? Clear? But we can mainly say, okay, it's only going to be things that are related that may lead to, yes, okay, increase in one will actually lead to increase in the other. That's okay as if those are directly proportional. Or you can say it's okay, increase in one may lead to a decrease in another. That's if they are inversely proportional. Whereas, okay, if parameters are unrelated, That will mainly mean that, okay, as the increase of one is not going to lead to either as okay, an increase or decrease of the other, and vice versa, because they were unrelated. Okay, so that's okay. It's not always going to be that say, okay, what is the relationship between this parameter and that parameter that they need to have a relationship? They can be unrelated. Okay, so to understand which parameters are related, which are unrelated, that's okay. That's going to be a must. But once they're related, then the second thing will be what kind of relationship do they have? Are they directly proportional? Are they inversely proportional? And in being as okay, inversely proportional, that was that sub relationship which we carry as okay. That could be reciprocal to one another. Clear? Any questions so far?
No.
Good. Now, the first parameter is okay that we will talk about is going to be period. Okay. Now, also just keep in mind, go that okay, as I will make okay, as we can say that okay, as this here. That is going to be okay, what we can call it okay, one cycle. Or we can mean this as okay, say one wave of sound. Clear, where we mainly can say, okay, what do we have? We have one point where it reaches to a peak. And we have okay, as one point where it reaches to a trough. But there's going to be as okay, one cycle, or mainly as okay, just one wave. Okay. Now when we say it's okay, period. The first two words mainly as okay, or three words, mainly as okay, it tells us what it is. So it is time. So this means as okay, going to be something that is okay, be expressed in terms of time. Where we can say okay, that the unit that will be as okay, any unit of time which is going to be second. You can even say it's okay, minutes, you can say milliseconds, you can say microseconds, whatsoever, as long as it's going to be expressed as a unit of time. That's going to be as okay, the unit of period. So it's okay, a period that's going to, it is the time that it takes for a wave to be produced. Or we can mainly say, okay, is the time from the beginning of one wave to the beginning of the next. Because this happens to be one wave. Now, yes, okay, we may actually, it's okay, have, let's say, it's okay, it's being followed by another wave. Clear? Where we can mean it says, okay, the time from here to here, or from the beginning of one wave to the beginning of the next wave. This measurement here is okay, when measured in terms of time, using a unit of time is going to is okay, be the period of this wave here. There's the same as okay, may apply for this one here. from beginning of this wave to, we can say it's okay, to the end of this wave, or we can say it's okay to the beginning of the, let's say it's okay, another wave. When we measure from here to here in terms of time, and so how much time did it take? That will become the period of this wave. And so for this wave here, okay, where we can say is okay, from the beginning of this wave or cycle to the end of this cycle, or we can say, okay, where we mean is okay, we'll say, okay, at the end of the cycle, we may is okay, let's say it's okay, another wave, another cycle beginning. Then this time taken here is going to be the period of this wave or cycle. Did that make sense? Okay, so we can say is okay, it can be defined as the time, okay, from the beginning of a wave. No, as okay, this for wave here can also as okay replaced by cycle to the end of the cycle. Or which also could be as okay VB. Or we can say as okay, the time from the beginning of a wave or cycle, okay, to the beginning of the next wave or cycle. Clear? Whereas, okay, yes, in this statement here, it's okay, it's me, yes, okay, just saying, yes, okay, we have this wave here. So what is going to be as okay, the time that it takes from the beginning of this cycle or wave to, let's say, yes, okay, to the end of the cycle or wave. That time that it takes from here to here, that's going to be the period. Whereas, okay, as if you look at this statement here, that's mean it's okay, it's going explaining the same thing, but I mean it says okay, it's going to be as okay, the time from the beginning of a wave. So we can again say it's okay, from the beginning of a wave or cycle to the beginning of the next wave and cycle. Because this is then going to be as okay, the beginning of the next wave and cycle. By Romania says, okay, what is this time I'm going to be accounting for? Still, yes, okay, the same period. Did that make sense? So all depended upon, yes, okay, how much it takes a cycle of one sound wave to complete. That will be the period of that sound wave or cycle. Did you girls get that? Clear? And it's mainly as okay because it is measuring the time. It's going to be expressed in a unit of time. Did you girls get that? Now you can take that unit of time and say, yes, okay, years. Don't do that because you're going to end up with okay, as a super crazy huge number. But you can even say minutes, that's even going to be as okay, a huge number. Clear? You can even say a second, well, okay, a big number, but not as big as okay as a minute. Okay, but usually that's okay. We may as okay say that the PA can be expressed in seconds, milliseconds, and or microseconds. Why we go for is okay the fractions of seconds. We'll talk about that later. Or commonly. Okay. Mainly because okay, a lot of cycles, a huge number of cycles of sound wave are going to be as okay completed in a second. So you may have okay as several hundred, several thousand, or several thousand, or even as okay millions of cycles completed in a one period or in a period of 1 second. Or we can say okay, several thousands or millions cycles completed in a time span of 1 second. So that's why as okay, each cycle is then going to have a period which is going to be 1 millionth, or as okay, 1,000th of a second. Because when we say period and period only, that is going to mean as okay, just account for how much time does it take for one cycle or one wave to get completed. Clear? That it was only one cycle or whether it was going to, yes, okay, so from the beginning of that cycle to the end of that cycle, this time span here, beginning and end, that is going to be as okay, the period. Clear? I already said, well, okay, this is the beginning of one cycle, and where it ends, that's when, yes, okay, when another cycle is going to begin. Mainly because you may have, okay, as just, okay, sound keeps on getting produced. There's going to be cycle, or it's going to be wave after wave after wave after wave after wave after wave. Clear? Okay, so where you say it's okay from beginning of cycle to end of cycle, that's going to be the period, or from the beginning of one cycle to the beginning of the next cycle, it's still going to be a period. Because where one cycle ends, that's where okay, as the next cycle begins. Did that make sense?
Yes.
Right, okay. Or you may say, well, okay, yes, what is going to be as okay, the period of my program that you signed up for? Clear? They may say, well, okay, it's going to be a period of 2 years. Well, it's okay, in your program, you may have, let's say it's okay, 4 cycles. Did that make sense? But you then will say, well, okay, it's going to, let's say, just roughly speaking, each module is 1 cycle. So you can say, okay, your first cycle was.
Could you say that again?
No, I don't. Sorry, girls. Okay, so you can say as okay, what was your cycle bio 101? You can say that was okay from day 1, and okay, that's the first 3 months. Clear? Okay. Then you go as okay, then what about physics? That's the next cycle, right? But we have bio 101 finishes from the first day 1 to end of bio 101. That was the period of the first cycle. So after that comes physics. Okay, so you can still say, well, okay, the duration of bio 101 is going to be from day 1 to the day we start physics. Okay. The duration or the period for physics is going to be from the beginning of physics. Did we start physics? So that's okay to the day that you girls begin your first scanning module. So that's going to be the period for physics. Or you may say, okay, yes, we start period at this date, we end physics at this date. Or we start physics at this date and we end physics at this date. That's going to be the period for physics. You can put it that way, or you can say, okay, from the day we start physics to the day that we start whatever next scanning module, let's say vascular. Now it becomes, okay, your period for physics. Did that make sense? Did that make sense, girls?
Yes.
Good. Any questions? Okay, so here, yes, okay, it is going to be expressed as a number. But number is made as, okay, just a digital number. Clear? Okay, we can say 10, but unless it's okay, you don't supplement it with a unit, 10 means nothing. 10 is just a number. Once you say it's okay, 10 seconds, you say, okay, now we mean that, okay, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that was 10 seconds. Clear? Did you girls get that? Okay, ladies. Okay, so yes, okay, it means that's okay, that's going to be expressed using any unit of time, whether you say it's okay, the basic was seconds. Okay, you can, okay, yes, multiply the seconds, and okay, yes, you may say minutes. You may, as okay, divide seconds, and okay, yes, you can have centiseconds. You can have, sorry, one quad. You can have milliseconds, or you can have microseconds. Clear? Now, girls, comes. Now, yes, okay, as I said earlier, yes, okay, for these things, yes, okay, whenever you come across something that says, okay, what is the typical value? Okay, these typical values that you will be given in the book, I mean, yes, okay, going to, yes, okay, what would be the typical value or whatever parameter factor exactly we talk about that is going to be, it's okay, be relevant to ultrasound. Okay, now the typical value of a period for ultrasound is going to be 6 raised to the power minus 8 seconds. 2, 5 raised to the power minus 7 seconds. Now we can mainly say that, okay, so this is mainly as okay, going to be recognized, okay, the normal range. Okay, where this means as okay, this is going to be as okay, the shortest period. And we can say it's okay, this over here is going to be as okay, the longest period for an ultrasound view. Is that clear? Now, let me just break this down as okay, 10 multiplied by, no, sorry, 6 multiplied by 10 raised to the power minus 8 seconds. Because, okay, what that mainly is, okay, means is, we can say as, okay, 6 is 6. Yeah. Now this 10 raised to the power minus 8. Let's just do it this way. Is 10 raised to the power minus 8. Now what thought this minus 8 is, okay, mainly makes it is going to be, it's okay, a fraction. Or we can say it's okay, a decimal number of a second. How many? Mainly it's okay, we said that, okay, as if we put 0, we put a decimal, and then we put, actually it's okay, we just put 1, 2, 3, 4, 5, 6, 7 seconds. Right, okay. Because this 7, okay, 10 raised to the power minus 8 actually is okay, it got translated into this. And we can mean it's okay, seconds is just going, it's okay, be seconds. Did that make sense? Now, we can also say that, okay, yes, this can also be expressed as 10. Or we can say it's okay, 6. Now we can mainly say that, okay, yes, multiply by 10 raised to the power minus 6. Okay. Now we had, okay, as being microseconds. But we stay as, okay, short of 2 decimal numbers. So that's why we can mean it says, okay, it becomes this. So it's okay, 6 point, or it can be as okay, 0.60 microseconds. Okay. Yeah, okay, as this here 0.06 actually is okay, accounts for these. But then we just okay, just express it as microseconds. Or you can even go and say 666, but then we go multiply by 10 raised to the power minus 3. And now we actually is okay, we can say it's okay, are going to be short of 5 decimal points. So that's going to be, it's okay, 0. And then it's going to be milliseconds. But they all mean the same. Or we can say it's okay, their worth is the same. Clear? If you want to, it's okay, express it in nanoseconds. Now then it's going to be as okay, 6 to 60. And we can say it's okay, nanoseconds. Anybody confused? That was just conversion of, okay, that's one basic V. Okay. So we could write it as this value here. 6 multiplied by 10 raised to the power -8 of a second. Where, okay, as multiplied by 10 raised to the power -8, what does that mean? Mainly it's okay, it just means that one over this second. Or where 1 over is okay. 100 million actually is going to be as okay. This is expressed as an exponent. This is expressed as a fraction, and this is expressed in a decimal. Where you say, well, okay, I want to express it in milliseconds. Then milliseconds is going to be as okay. So microseconds. There's going to be difference of a second. Now, what's the difference between this exponent here and this exponent here? The difference is 2. And mainly because you went from a bigger or from a smaller unit and express its work in a bigger unit. Because, okay, this is just one fraction or one decimal number lesser than a nano. Or we express it in a bigger unit as okay. You're going to just okay divide the basic unit, basic number here. So you end up with okay as with a smaller number. Where the difference of these, this 8 here and this 6 here is okay, it's okay, just being converted into decimal numbers. And then we say, okay, that which was 6 times 10 raised to the power -8 seconds becomes 0.06 multiplied by 10 raised to the power 6 or -6 seconds. This 10 raised to the power -6 here is okay, it's not going to be that way. This number here is going to be as okay, the typical value of an ultrasound cycle or the minimum of an ultrasound cycles period in terms of microseconds. So you can say, okay, it's going to be 0.06 microseconds. Now here's, okay, this microsecond mainly means 10 raised to the power minus 6 of a second. If you don't want to express it in microseconds, you can say it's okay, I want to go on to milliseconds. Now, milliseconds is mainly it's okay, just because it's okay, 10 raised to the power minus 3 of a second. That's how we say it's okay, a millisecond. But then we actually, it's okay, we just have to, it's okay, add 3 more decimal numbers to what we already have. So this, as microseconds, now becomes 0.0006 milliseconds. Where you can write it as, okay, as milliseconds, or you can write it as 10 raised to the power minus 3 of a second. Clear? So the shortest period of an ultrasound second is going to be as, okay, 6 times 100 millionth, or 100, that's okay, 100 million, sorry, 100 millionth of a second. Did you guys get that? That this 100 millionth of a second then can be expressed as, okay, a different fractions of second. Just keep in mind, okay, as this number here is going to change. All dependent upon is, okay, whether you use a big unit or is, okay, that becomes a fraction of it. Or is, okay, sorry, a small unit. Or a big unit. A small unit. And not so small unit, but okay, so then it's okay, yeah. Very, 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 very small unit. Or what we mainly can say here goes. Is that what is it that? $60 multiplied by 10 raised to the power 9 means. Or we can say, okay, how does it become equal to this? Now just keep in mind, okay, this is going to be as, okay, nanoseconds. Oh, sorry, not nanoseconds, sorry. Seconds. Where we can mainly say, okay, this part here, that's the nano. But 10 raised to the power minus 9 actually means that we okay, convert this into 10 raised to the power minus 8 as we have here. Mainly would mean that, okay, yes, this number here is okay, will be divided by 10. So what do you get? 60 divided by 10 becomes 6. And then we say, okay, we just compare this. Take this 10 raised to the power minus 8 seconds. Where this 10 raised to the power minus 8 is 1 decimal greater than a nano. Second. But practically, yes, okay, the worth of all these numbers here, yes, okay, is they're worth at the same. They're just going, yes, okay, be expressed in different ways. These, I mean, is okay, just exponents using as okay, different fractions of a second as a unit. Okay. Right. Where we can say, okay, it can also be expressed as a decimal number. Why a decimal number? Meaning because it's okay, it is going to be a fraction of the basic unit that we expressed here, second. Now, if we reduce this unit here to, as okay, let's say milliseconds, then this number here is going to increase. It's not going to be 0.000006. Then we actually are going to just okay, take off. I guess it's okay, 3 zeros, because we said it's going to be as okay, milliseconds. Did you girls get that? So that's okay. For some of these parameters, yes, okay, we will have, yes, okay, because that's okay, this actually becomes a range because you have a minimum and you have a maximum. Clear? But the same alias, okay, just applies to the other one, which is going to be 0.5. Oh, sorry, 5 times 10 raised to the power minus 7 seconds. Clear? Okay, which we can mainly say, okay, is going to be as okay, 50 million of a second. Okay. Or we can say it's okay, half a microsecond. But you can go on and say, well, okay, yes, 5. Oh, okay. this 10 raised to the power minus 7 and second is second. Now, what does this 5 here means? 5 is 5. This 10 raised to the power 7 here actually is okay, means that you divide this by this. But then the unit still will be as okay, second. Now you can say, well, okay, this may be as okay, 1 greater than a microsecond. Okay, because okay, for microseconds, it was going to be as okay like this, and then okay, as the unit would be microseconds. So mainly as okay, this will mainly mean that okay, yes, you multiply this by 10. I'm sorry. You divide it by 10. So yes, okay, that becomes 0.5. And then you can say it's okay, either multiply by 10 raised to the power minus 6 seconds. But this 10 raised to the power minus 6 actually is okay, becomes the micro, and second becomes a second. Where we already said that, okay, as the unit for micro is mu. So we can say, okay, the greatest typical range of ultrasound value is, now what does 0.5 mean? That's just as a decimal, but if you express it as a fraction, it's going to be half a microsecond. So if you said, okay, this here is a period of 1 microsecond, or as a time span of 1 microsecond, and the period of, okay, as 1 cycle to be completed is going to be half a microsecond, you will actually have one cycle, and we can say it's okay, another cycle. 2 cycles completed in 1 second, a microsecond. Where, okay, as the period of each of these is going to be half a microsecond. Yep. Where we can also, yes, okay, say that, okay, this 5 multiply by 1 over, that's okay, 10 raised to the power. Or it's okay, or it's okay, 10 million, or 10 million. Okay, can actually, it's okay, be the same as, we can say it's okay, dividing 5 by 5 divided by the very same number. Yes, okay. 10 million. Okay. Why do we go divide? Mainly because, okay, this here already is okay, is a fraction. Or it is a decimal number. But we will only as okay multiply once we go. If we multiply it by the fraction, or if we multiply it by the decimal number. Or multiply by a fraction or multiply by a decimal number is me is okay going to be the same as okay dividing by is okay the reciprocal here. Or we can say okay the worth that decimal value. But then you just have to just okay make sure that okay if you do that, then you also change the unit accordingly. But basically, that's okay. Based on that, if we go with it, okay, yes, if that's the case, we can mainly says okay that the period or the max period of one cycle in ultrasound is going to be half a microsecond.
Can you say that again for me?
Huh?
I said, can you repeat what you just said?
Based on that, we can mainly say as okay that the period, the maximum period of one cycle in ultrasound is going to be half a microsecond. That's the longest time that it will take an ultrasound period to okay, an ultrasound cycle to complete. Because what was a period and a period only? The time that it takes one cycle to complete. Is that clear? Okay. The unit that is going to be expressed is going to be as okay a unit of time because what is it that a period is? It's all about the time it takes. What is completed in that span of time? One cycle or one wave. How do we know that one wave has completed? We can say as okay, we either as okay accounted from the point where that wave begins to yes, okay, where that point waves or wave ends. Clear. When we measure yes, okay, this in time, that becomes the period. Or we could say as okay, the period of let's say as okay, this wave here could be as okay from where it started to yes, okay, mainly as okay, where the next wave will begin. So that's okay. The period of our brown wave here is going to be this. If we measure it and it's okay in terms of time. Did that make sense? Now, since we say it's the time, is going to be, as okay, be expressed, it's going to be measured using a unit of time. Seconds, milliseconds, microseconds. You can even go nanoseconds if you want to. Clear. But the typical value was 6 raised to the power minus 8 second, 2, 5 multiplied by raised to the power minus 7 second. So as I said in the beginning, this is the shortest period because it's a greater fraction of a second. You broke a second down into, yes, okay, a greater number of pieces. Yeah, this is going to be, as okay, the maximum period. Mainly because it is a smaller fraction of a second. Why? Because you broke the second down into a smaller number of pieces. So this here, it's okay, became, you can say it's okay, 0.06 microseconds. Where over here, it's okay, this became 0.5 microseconds. Or we can say 0. And we still have, okay, this 0 for the micro. But then we just go on, okay, 2, 3, 4, 5, 6. It becomes the same. But the remaining is okay. Decimal numbers here means okay, there's going to be is okay the difference between the micro, which was 6 and 8. All the same applies here. But you can convert these micros into millis. Or even it's okay. If you want, it's okay into nanos. So here. But even it's okay, the longest period that it will take one cycle. The longest time that it will take one cycle to complete. When we talk ultrasound wave is going to be as okay, half of a microsecond. So what I mean, you have a second, you break that into as okay 1 million parts. And even that 1 millionth part of a second is broken into half. That becomes half a microsecond. That's the time it takes for one ultrasound wave or cycle to complete. Is that clear? That's the max. But if you take the other one, well, okay, that's 100th of a microsecond. Okay, that's mean is okay, what that 10 raised to the power minus 8 will mean. So 1/100th of a microsecond. But then you say it's okay, 6. So you can actually say it's okay, 600 microseconds is okay. Sorry, 0.60 is okay, the 100th of a microsecond. Is okay, 1 over. A 60 or 100th of a microsecond is going to be as okay, the minimum time span for a sound wave of an ultrasound to be produced. Any questions? Now, the next thing is just what is going to just okay determine the period of the sound. Or you can say it's okay, the cycle. Now, girls, just think of it that way. Right now, it is me who is talking. Right? Clear? Now, just assume that, okay, as each word that I speak is one cycle. Just roughly speaking. Clear? Now, if I speak slowly, so that you can follow along. What did I do? You can say it's okay, I stretch out the period, right? So it's okay, it took me, I took more time to just okay, speak out each word. Did that make sense? Whereas it's okay, on the other hand, I can say it's okay, I go super fast so you can't follow along. What did I do then? I reduced the period that I took to pronounce each word. Some of you might even not have caught what I said. I mainly said, okay, yes, I'm just going to just okay, decrease the period of each word so that you can't follow along. But it was me who was speaking these words or producing each wave here. So it's mainly as okay, going to be the source that will determine the period or the cycle. Is that clear? Okay. Now, for now, girls, just remember source is enough. At this point, we can say it's okay, source, that will be enough. What we will realize later on in some later chapters, that it's actually going to be as okay when we say source, because what did we say that source could mean? It could either mean the transducer or it could mean the system, right? But it's going to be as okay, your transducer that would be determining the factor, or you can say determine the period. It's going to be as okay, the transducer that be as okay, the component of your system, of your source that will determine the period that it will take for each cycle to complete. Did you girls get that? Did that make sense?
Yes.
Okay. Now, adjustable. Now, what did we mean by adjustable? Well, that's something that you could change. Well, practically, yes, okay, you can, if you use a different transducer. But what they mainly say, or what they mainly talk about here is that no, the period cannot be changed if you use a basic ultrasound system. And with a particular transducer. Now, if you change the transducer and that transducer has a different period, then as the period will change. So that's why I said, but we will realize that later on, that the period of a sound wave is going to when we say it's determined by the system or source. The actual part of the source that's going to determine the period will be the transducer. Did you guys get that? So if you don't change the transducer, there's not going to be you can say a knob or a button or so and so and so on your system that you may play around with, which is going to change the period. If you want to change the period, you need to change the transducer. Is that clear? So as such, yes, it is not adjustable. Unless, yes, you change the transducer. Any questions, girls? No? KK. Well, that was one of the 7 parameters. At least that's what we may be dealing with for now. Okay. Now go get some fuel. And when we come back, yes, we will talk about our second parameter, which is going to be frequency. Okay, goals. Let's see if we can talk about what frequency is. And let's see if it has some relation. Now, goals, one thing about here, the typical value. That is going to be we can say you have to remember that. The typical value of your period. That's going to be something that you have to remember. Okay. So that's from time to time, that's most likely that's when it's going to be relevant, I may ask, so what was the period? Or what was the typical value of a period? Okay, so you have to be able to say that, yes, it is yes, 6 multiplied by 10 raised to the power minus 8 of a second. 2, 5 multiplied by 10 raised to the power minus 7th of a second. Or you can say it's 0.06 microseconds to 0.5 microseconds. Or whatever. But this typical value is it is going to be expected that you know that. So it's just going to be as okay a value that you need to remember, just like okay, your birthday. Or your last four of your social, or it's okay, the phone number of your workplace or something like that. Okay. Now a tip to remember is okay, you just say it out loudly 10 times. And from time to time, it's okay, you will just have to, it's okay, repeat it yourself. Don't worry about it. I'm going to make you guys repeat it. Okay. Okay, girls. So see you girls back at 1 o'clock, okay? For the frequency. Okay, girls, welcome back. Okay. Any questions so far? Any questions? Nope. Now we can make the SOK, just go on to SOK, our second parameter, which is frequency. Okay. Now generally, not necessarily is okay just for sound waves and so on, so on, so. But we can say it's okay. Generally speaking, it's okay. What frequency mainly or mean is how many times is an event occurring in a specific period of time. Or if you can put it this way, that occurs. A frequency is number of events, or we can say number of an event. Per unit of time. Clear? No, we can say it's okay. We can say it's okay. An example, we can say it's okay, number of tests per month. That is going to be as okay, the frequency of tests. Okay. You're going to say the number of breaks per session of, let's say, 3 hours. So if you had a class session that was lasting for 3 hours, the number of breaks that you're going to get in these 3 hours is going to be as okay, the frequency. Did that make sense? Now, what you mainly, yes, okay. Clear? So, if we now take this as okay and say it's okay, what is going to be as okay, the frequency of a sound wave. Now, the frequency of a sound wave is going to be as okay, we can say that would be as okay, the number of cycles. Now, we also say that okay, the cycles, and we also can say it would be as okay, waves. Okay. Now, that number of waves or cycles, now cycles or waves, that's going to be as okay, an event. And the number of that event per a unit of time, right here is going to be as okay. For us in this case, it's going to be seconds. That is going to be as okay, what we will call the frequency of the sound wave. Yeah. So we can put it this way and say it's okay, if we had, now this time span here is okay, maybe let's say, just to make it simple for now, 1 second, for instance. Yeah. Now, if in this 1 second here is okay, we have 1 cycle, 2 cycles. What do we have? The number of cycles. Is going to be 1, 2. What did we have? This was 1 cycle, this is another cycle. Or waves in a period of 1 second. So in this case, here we can mean it says, okay, the frequency is going to be 2 cycles per second, or this cycles per second here can now be as okay translated into hertz. So our frequency is going to be as okay 2 hertz. Did that make sense? Did you girls get that?
Yes.
You said one frequency is 2 hertz.
Warm it up.
Did you say that one frequency is 2 hertz?
No, why would one frequency be 2 hertz?
I thought that's what you said.
That's the look. What were the number of cycles that we had? We had 1 cycle, we had 2 cycles. Clear? So the number of cycles is 2. Clear? That was completed in a time period of 1 second. That means that, okay, this blue line here is, okay, what does it represent? A period of 1 second. But in 1 second, we had 2 cycles completed. Clear? So 2 is the number of cycles. Clear? Clear? Where, okay, the cycles per second actually is okay, will be equal to, is okay, what we will say hertz. So if 2 cycles were completed in 1 second, yes, okay, your frequency is 2 hertz. We can take another example and see Now, if this here is okay, still is 1 second. This time span here is still 1 second. But if in this 1 second here is okay, what we have is six. Now we can immediately says, okay, now how many cycles do we have? 1, 2, 3, 4, 5, and 6. So the number of cycles that we have now is 6 cycles. Which are completed in a period of 1 second. So we can say that, okay, yes, 6 is still 6. This number here is okay, or we can say, okay, the number of cycles per 1 second becomes hertz. So our frequency now is 6 hertz. Did that make sense?
Yeah.
Clear? If we said, okay, yes. If you, for instance, say, okay, yes, this period here, for instance, was not 6 seconds, but actually that's okay. Let's say that we made it 10 seconds. Okay. That's going to make it confusing for you guys right now. That's fine. But have you said, okay, yes, had it been, let's say it's okay, 60 cycles. Now I'm not going to be sitting here and just okay, draw 60 cycles. Okay. But if you said, okay, yes, what we may have done here was going to be, that's okay, 10, 20, 30, 40, 50, 60 cycles in second. And your frequency would have been 60 hertz. Did that make sense? Or however you said, okay, yes, had it been in thousands, and not only is okay, did you have 60, not only 100, but actually that's okay. 6,000 cycles per second. Clear? Then we could say that your frequency downward back, yes, okay. Obviously, 6 is 6. This 1,000 here is okay, may become this. And hertz is still hertz. Where this will be as okay, 6,000 hertz. Or it can become, I can still be read as 6. Now 1,000 times is kilo, right? So it will become 6,000 hertz or 6 kilohertz. Did you get that?
Yeah.
Clear? Likewise, okay, if this had not been, okay, I'm not going to be sitting here and drawing as, okay, 2,000 cycles. But you can say as, okay, if there had been, yes, okay, 1,000 cycles and another 1,000 cycles. So we had a total of 2,000 cycles in 1 second. That would mean, yes, okay, we could say, okay, 2,000 cycles per second. That will be the frequency. But this 2,000 cycles per second could become 2. The 1,000 here will become this. Or it could also, yes, okay, be this. And then, yes, okay, the thing, yes, okay, cycles per second will become hertz. So you can say, okay, 2,000 cycles of waves of a sound completed in 1 second is going to be a frequency of 2 kilohertz, or 2 multiplied by 10 raised to the power 3 hertz. Did that make sense? So yes, okay, like you can go from kilos, you can go to megas. Where it's not going to be just, okay, 1,000, but it's going to be just, okay, 10,000 or 1 million. So you can still say it's okay that we had 2 million cycles completed in a second. That would mean it's going to be as okay that 2 is still going to be 2. But then this is okay. Could be as okay 10 raised to the power 6. Or mega. And cycles per second is still going to be okay, we translate it into the same parts. Did that make sense? So what did that tell you? That the more number of cycles or waves of sound, waves that occur in a second, the greater is going to become the value of your frequency of that sound wave. Did that make sense? So which was a greater frequency, 2 kilohertz or 2 megahertz? Which of these two frequencies was going to be the biggest or highest frequency? 2 kilohertz or 2 megahertz?
2 megahertz.
2 megahertz, because we are saying 2 million cycles are completed in 1 second. Clear? Where if we say 2 hertz, just 2 cycles per second. 2 kilohertz, 2,000 cycles per second. Okay. 20,000 hertz, 20,000 cycles completed in a second. Did that make sense? Okay, so our unit for frequency is going to be hertz. H-E-R-T-Z is how you spell it out. H as in happy, Z as in zebra is the symbol for hertz. Okay, where if it is preceded by a prefix K, it becomes kilohertz. If it is preceded by a prefix M, it becomes megahertz. And okay, yes, although yes, okay, you're probably not going to see it, but never say never. If it is if the hertz is preceded by, it's okay, a unit of G, it becomes gigahertz. Okay. Now goes in ultrasound, yes, okay, the unit that you may see is going to either, yes, okay, kilohertz or megahertz. Okay. If it is given as, okay, as a, in turn, as, okay, unit, the unit kilohertz is going to be as, okay, a bigger number. Because, okay, commonly as, okay, your ultrasound is, okay, will be expressed using the unit megahertz. But what does megahertz means? 1 million cycles per second. 3 megahertz, 3 million cycles per second. So 3 just gets transferred. Million becomes a mega, and hertz becomes a hertz. But the hertz mainly is, okay, just is the representative of the unit frequency, which represents, or which is accounting for the number of cycles of an event occurring in a second. Since here is, okay, we say frequency and frequency only, that's just going to be accounting for how many cycles did we have in a second. Did that make sense? Did that make sense?
Yes.
Any questions? Okay, so if I say a sound wave has a frequency of 20 kilohertz, what does that mean? That there, okay, has 20,000 cycles completed in a second. Capish? Now, girls, the typical value. And please keep in mind, go, yes, okay, this is going to be, yes, okay, we can say, it's okay, the typical value. That's okay, that's going to, that's okay, be relevant for ultrasound. There may be other kind of sounds around us, which have other typical ranges. But the value here that we are given is made as, okay, going to, yes, okay, what are going to be as, okay, the typical value of the frequency of a sound wave for it to, yes, okay, be used as a source of ultrasound. So it's going to, yes, okay, it's going to be a range which is going to be, yes, okay, 2 to 15. And here it's okay, the unit is mega hertz. So what would that mean? That 2 is 2, and mega is a million, and hertz is hertz. 2 is okay, all the way to is okay, 15 million hertz. Clear? What does this 2 million megahertz, or what does this 2 million hertz, sorry, mean? That may mean that it's okay, that's going to be as okay, 2 million cycles per second. Whereas, okay, as here, 15 will mean that, okay, that's going to be as, okay, 15 million cycles per second. Now, girls, please. This here is okay, that is going to be as, okay, we can say it's okay, the lowest frequency of an ultrasound transducer that can be used for ultrasound. Is that clear? Where we mainly can say that, okay, yes, this one here, that is going to be as, okay, the highest frequency of ultrasound that can be used for an ultrasound transducer. Okay. Can we have sound waves that are going to be as, okay, of a higher frequency than 15 million? Yes. There may be sound wave which has, okay, yes, 150 million cycles per second. Or we can say, okay, 150 million hertz. But can we use that for ultrasound? No. Why? That's going to be as, okay, a later discussion. Okay, girls? Now just look carefully. Because, okay, we say, now I'm just going to just, okay, go more specific with the colors. And say it's okay that this and this here was 1 cycle or 1 second. And likewise here. We say that, okay, this line here is, okay, measured a time span of 1 second. What would that now mean? That, okay, as if we had a frequency of 2 million, which was the lowest frequency. Clear? We will only as, okay, and I say only as, okay, have. Now just assume that, okay, as this here is going to, yes, okay, this 1 cycle here. Oh, sorry. Is going to, yes, okay, each of the cycles that I make is going to, yes, okay, account for 1 million cycles. Okay, but we can mainly say, okay, that we mainly is, okay, we just have one, 2 million cycles per second. Clear? Did that make sense? Yeah, here we will have total of 15 cycles. So what do we see? That where we had just 2 million cycles per second, which was the lowest frequency. We can actually say, okay, that's when we will have, okay, as the greatest period. which actually is okay, say was going to be as okay. Half of a microsecond. Where here is okay when we have 15 million cycles per second. That's going to be as okay where we have the lowest period. Which was going to be as okay 0.06 microseconds. Did that make sense? So we're going to come back to this one here in just a second. Or maybe just in a little bit. What you guys may see is okay where this is going. This is made as okay, just establishing the fact that period and frequency are related. And what kind of relationship do they have? We said when the highest period, oh yes, okay, the lowest frequency had the greatest period. And the highest frequency has the lowest period. That they are inversely proportional. Right? If your period is, or if the frequency is greatest, and in that instance, okay, you will have the lowest period. That makes frequency and period inversely proportional, right? Where you had the lowest frequency and the period of each cycle is going to be greatest. That makes that inversely proportional as well.
Here's what I found from teachmodio.com.
No, I don't want you to talk about that. Yes. Who's getting a migraine? Okay, girls. Now we can then say, yes, okay, what's going to, yes, okay, determine this factor here, parameter, sorry. We can come back to these in just a second. But this thing is, okay, is going to be determined by the source. Clear? And goes, that's okay, what I mean by source here is mainly as okay going to be as okay transducer. So what your different transducer are going to be, yes, okay, they are going to, yes, okay, be coming with a fixed range or fixed frequency. So out of, yes, okay, most of our ultrasound system, yes, okay, what is going to, yes, okay, determine the frequency? The source. Did that make sense? And for this case here, it's okay, will be transducer. Now the next thing, and I know that, okay, yes, now your book says it. Is it adjustable? And just listen, girls. Although your book says no, but that explanation for no is what is given. Clear? So the explanation where is okay, a matter of okay, as whether you can adjust the frequency is no, is while using a basic ultrasound system and transducer. So it's only going to be no, yes, okay for basic ultrasound system and transducer. Okay, girls? And nowadays, as okay, we mainly says, okay, the ultrasound systems that we have are not just basic ultrasound systems. So it's actually, it's okay, going to be yes. So it is adjustable. Why? Or it's okay, we can say, okay, for updated. Or what we later on as okay, will refer to as broadband transducers. Okay, now some of you may scratch your heads and say, so Mike, what do we answer if you ask us, is the frequency adjustable? But if I say is the frequency adjustable, and I don't provide you any further information, you can say, well, okay, that can't be determined. I don't know whether to say yes or no, because I need more info. Did that make sense? But if you are being asked, using a basic ultrasound system and transducer, is the frequency adjustable? Your answer would be no. Whereas if I say it's okay, using a broadband, now what the hell a broadband system is going to be, or transducer more correctly, that's going to be, it's okay, chapter number 8, that we talk about that. Clear? Okay. But it's okay, in that instance, that's okay, you can say it's okay, using it's okay, a broadband transducer, is the frequency changeable or adjustable? Yes. Okay, and that's actually, that's okay, where your system, the machine may play a part. Because, okay, you can change the frequency on your system that may be a child transducer. Well, okay, you need buddy, go and produce sound waves by this frequency here. So what was the frequency? How many cycles were completed in a unit of time? Clear? That unit of time is fixed. He says, okay, that unit of time that we're going to be using is going to be 1 second. Clear? So if 1,000 cycles, that's contagious. If 1,000 cycles are produced in a second, that will become a frequency of 1 kilohertz, or 1,000 cycles per second. Okay, 2,000 cycles per second, 2 kilohertz. 2 million cycles per second, 2 megahertz. But on the other hand, we can also see that, okay, yes, frequency and period are inversely proportional. Or let's do it this way. Maybe not that extreme examples. We can say it's okay if this here is 1 second. Okay, we'll just label this one here as A. We can also say down here is okay, we have a period again. That's going to be, it's okay, 1 second. Clear? And that will be B. Did you ladies get that? Clear? Now, if we said that, okay, here in 1 second, we have 1 cycle, 2 cycles, and 3 cycles completed. That will mainly mean that, okay, yes, the period of each of these cycles here is going to be, where's the green, the pink, or the orange? The period of each cycle is going to be, it's okay, 1/3 of a second. Because 3 cycles were completed in a second. Clear? Since we have, okay, as 3 cycles in a second, we can mainly say, okay, that for A, the frequency is 3 hertz. Did that make sense? Now goes for B. So here we actually has, okay, have 1 cycle completed, 2 cycle completed, 3 cycle completed, 4 cycle completed, and we have, okay, as a total of 5 cycles completed. So based on that, we can mean this, okay, since there's 3 cycles, 5 cycles completed in a second, that's okay, our frequency will be 5 hertz. Did you guys get that?
Yes.
Okay. Which mainly will mean that now, yes, okay, if we were able to, yes, okay, if we are able to, sorry, complete 5 cycles in a second, that will mainly mean that, okay, yes, the period for each second, or for each cycle, sorry, is going to be, it's okay, sorry, 1/5 seconds. Clear. Or where we mainly, yes, okay, also could say here is that of these two examples here, is okay, that's where we have okay as the highest frequency. Let me just here we have the highest frequency because we have the shortest period. And or here we have okay as the lowest frequency of the two because we have the greatest period. Okay. So what does that tell us? That mainly is okay, establishes as okay, the thing is that frequency is inversely proportional to period. Because the greater the period, the lower the frequency. The lesser the period, the greater the frequency. But then when you also says, okay, look at this. Because, okay, this hertz here mainly means how many cycles per second. Or if you say it's okay, if you take this number and multiply by this, just like you take this number and multiply by this, what do you get? 3 multiplied by 1 over 3. What do you get? You get 1. You say 5, which was the frequency, multiplied by 1 over 5. What do you get? 1. So what does that establish? That establishes that, okay, not only are period and frequency inversely proportional, but they are also reciprocal. Did that make sense? Doctor, that is contagious. Did that make sense?
Yes.
Good. So not only are they inversely proportional, but we can also say as okay, the more you increase the frequency, the shorter is it that the period is going to be, or the other way around. Okay, so not just only as okay inversely proportional, but actually as okay reciprocal. Now, those of you who have their cameras shut off, turn them on, or you'll be marked absent for the session. Those of you who have your cameras off, turn them on, or you'll be marked absent for the session. Last call. Those of you whose cameras are off, turn them on, or you'll be marked absent for the session. Okay. You were warned. Now girls, what do you mean to be reciprocal? Let's just do it this way. And say, yes, okay, this period here was not 1 second. Let's say that, okay, yes, it is a millisecond. Did that make sense? So if this period here is a millisecond, what do we have now? We would have 3 cycles completed in a millisecond, which may mean have we been recording this frequency here is okay for a whole second. You have completed 3,000 cycles. So the frequency actually would have become a kilohertz. Clear? And since we are able to just, okay, complete 3 cycles in a millisecond, that mainly is, okay, would make the period of each cycle 1/3 of a millisecond. So what do I say here? This is reciprocal to a milli. Because a kilo, that was 1,000. A milli was 1/1,000. Did that make sense? So if we had 3 cycles completed in a second, a millisecond, that means, okay, we'll make the frequency 3. The number of cycles completed per millisecond now is going to become kilohertz. Where we can say, that's okay, all of this, cycles per second is still hertz. But the reciprocal of milli is a kilo, which goes here. Which means also could be read, okay, we completed 3,000 cycles in a second, which became as, okay, a frequency of 3 kilohertz. If we change this period from a milli to, let's say, it's okay, a microsecond, which may mean that, okay, as if we completed 3 cycles in 1 microsecond, then our frequency is going to become 3 megahertz. Why? Because mega was 1,000,000, right? And a micro was 1/1,000,000. Or if we said that 3 cycles were completed in 1/1,000,000th of a second, that would actually mean that, okay, as the period of each cycle was going to be 1/3 or 1/300 of a millionth of a second. Clear? So the time we just, okay, increase the frequency, the shorter and shorter and shorter is it that the period will become. So if you are being asked, that's okay that you have a transducer which has a frequency of, let's say, 2000 hertz. Or if something has, okay, has a frequency of 2000 hertz, and they're asking us, okay, where is the period? That is going to be, okay, 2 or 1000 of a second. I'm sorry. Sorry. 1 or 2000 seconds. Sorry. Because that's okay, your period multiplied by the frequency is always going to be 1. Or we can say the values, which is going to be 1 over 2000. Multiplied by 2000, it becomes 2000 multiplied by 1 divided by 2000. But you can say 2000 divided by 2000 is 1. Or this cuts out this and you end up with 1. Or you can say it's okay, since the frequency was 2000 hertz or 2 kilohertz, the period is going to be as okay, 2 milliseconds. Because milli and kilo are reciprocals. Did that make sense? So when I went on in chapter 1 and said, well, okay, as these units here are reciprocals to one another. Or we can say it's okay, fractions and multiples are reciprocal. As a kilo is reciprocal to milli. Micro is reciprocal to mega. Okay, you can say centi is reciprocal to hecto. Deci is reciprocal to deca. Giga is reciprocal to nano. So when we say, as okay, if something has a frequency of XYZ amount of kilohertz, its period is going to be XY1 over XYZ milliseconds. When you say gigahertz, microseconds. Any questions? Okay. We still haven't got to yes, okay, why we still call it ultrasound. So we'll talk about that tomorrow. Clear? Okay. So we will still be talking of frequency and period tomorrow. When we get there. Okay, girls? Any last question? No? Okay, Duck. Then I see you ladies tomorrow. Okay, girls?
Thank
Have
you.
fun.
Thank you.
Bye-bye,
Thank
girls.
you.
Take care.